Swayam Prabha. Digital India. Educated India.
Welcome back everyone. We are learning the basics of building construction, and today we are going to dive into deep foundation, which is the last part of our module 1, which was on foundations. The previous lectures were on shallow foundation, where we learned about the different types of shallow foundation and also on the formula used to calculate the size of footings. Today we are going to learn about the different types of deep foundation with a particular attention to pile foundation. Now, what do we mean by deep foundations? This type of foundation, the depth is larger in comparison to its width, and it does not require open pit excavations to construct. As a result, it is not called open foundation like the shallow foundation. This type of foundation can be mainly put into 3 categories. First is pile foundation, followed by pier, and then caisson or well foundation. Now, the pile foundation is the most commonly used for construction of buildings. For the purposes of this lecture, we are going to study pile foundation, caisson and cofferdams. Pile foundation is defined as a series of columns which are constructed or inserted into the ground to transmit the loads of a structure to a lower level of subsoil. Now, pile foundation can be used when suitable foundation conditions are not present at the near ground level. So, we are going to have to make deeper foundation than the traditional shallow foundation. Now, this situation may happen due to various reasons. For example, the subsoil has low bearing capacity, the water table is very high, there is presence of layers where highly compressible subsoils are there and it is not sufficiently consolidated, and the subsoil which may be subjected to moisture movement or plastic failure, that is, for example, black cotton soil, which we had studied in the last lecture. Now, we can classify pile foundation into various types based on its basic function or how it operates, and also on the basis of materials of its composition and the method of construction that is used to make the pile foundation. So, it is going to be a lot of terms we are going to learn today. So, it is best for you to note them down so that you can at least revisit the key terms and study about them further later. First of all, we will learn about the classification on the basis of function. So, what are the types? End bearing pile, friction pile, compaction pile, tension or uplift pile, anchor pile, fender and dolphin piles, batter pile and sheet pile. So, we are going to learn about each of these briefly. Now, based on the composition and the method of construction, you can also see that there are concrete piles, timber piles, steel piles and composite piles. We are going to pay particular attention to concrete piles in today's lecture. On the basis of function, let us revisit the types and learn about them, each of it in detail. The first one is called end bearing piles. Now, as the name suggests, this type of pile transfers the load to the hard stratum at the bottom. So, obviously, this particular type of pile has some attachment at the bottom which helps it to anchor itself to the subsoil or the hard strata and helps to support the building. The friction piles transfers the load through the screen friction. So, that means the surface of the particular pile is of greater importance. It will probably be corrugated or rough to help it to anchor the building with the help of friction. Compaction piles themselves do not transfer load. They are usually used to compact granular soil. They are mostly made up of sand. We are going to study sand piles towards the end of the lecture today. So, mostly we need to learn that they do not transfer load but help to hold the ground together and support the building above it. Tension piles help to anchor down structures to prevent uplifting or overturning. Anchor piles provide anchorage from horizontal pull. Fender and dolphin piles protect the sides of the building and prevent it from being hit by ships or floating objects. So, that means this type of pile is very commonly used in next to large water bodies like sea. Sheet piles provide impervious layer and reduce seepage. So, if we want to create some construction in the middle of water and we need to create a watertight area, we can go for sheet piles. This too we are going to visit towards the end, especially with respect to the construction of cofferdams and caissons. Batter piles are used to resist large horizontal or inclined forces. So, this is how we can actually differentiate between various types of piles on the basis of functionality. In today's lecture, we are going to take a look at a lot of concrete piles, many of which can be categorized as either end-bearing piles or friction piles, and we are going to see each of them and try to understand how they are working. There you will be able to see how this functionality is actually being practically applied. Now let's start categorizing pile foundation on the basis of materials and the method of construction. The first thing we are going to visit today is concrete pile. Now concrete pile can be further subdivided into various types. The first is if we go for precast pile, that is the pile is actually created off the site, brought to the site and installed. The other is cast in situ pile. So this, as the name suggests, is created in the site itself. Now cast in situ pile can be further subdivided into two types based on the way it is installed. The first is called driven piles. Now as the name suggests, it is driven into the ground. So we will require pile driving equipment to hammer it and drive it into the ground. Board piles, on the other hand, are not driven into the ground but are gradually created with the help of boring out the ground and then gradually inserting concrete into that space. Now board piled and driven pile can further be subdivided each. Driven pile can either be cased or uncased. What do we mean by this? Cased means that the pile has a certain casing or a covering, a surface that basically separates itself from the ground. The uncased piles do not have any casing. Board piles can be further subdivided into pressure pile, under-ream pile and board compaction pile. One of these terms should be familiar to you, under-ream pile foundation, that we studied in the last lecture when we were visiting the type of foundation used in black cotton soil. Today we are going to look at it in detail once again. Now coming back to the other material that we can use, timber piles. So timber pile is also used in certain specific locations. We are going to visit that. Steel piles can be further subdivided into edge piles, pipe piles and shape piles. So it becomes clear to you that it's basically a division on the basis of shape. It can either be edge shaped, pipe shaped or sheet shaped. Composite piles are a combination of two materials. So it can either be a combination of concrete and timber or it can be concrete and steel. Today we are going to first take a look at concrete piles. Concrete piles are highly durable and very high capacity. It can take a lot of tonnage of load. They can be classified into two major types, namely precast concrete pile or cast in situ pile. And cast in situ can be further subdivided into driven, that is cased or uncased driven piles, board piles which can be pressure pile, under-ream pile and pedestal piles. Concrete precast pile. This is manufactured in a factory and it requires very heavy pile driving equipment to install it on site. They may be square, octagonal or round in cross section. They may be tapered or they may have parallel sides. They usually have reinforcement inside it. They can take up maximum design load of about 80 ton. They can vary between 30 to 50 centimeter in diameter and go up to a depth of 20 meters. The figures represent how we can have square, octagonal, round, etc. precast piles that have reinforcement within it. How do we create these piles? In the factories, the formwork of the required shape is first prepared. The inner side of this formwork is coated with soap solution to make it not adhere to the sides of concrete. Reinforcement cage is then placed inside, ensuring that proper cover is all around. The cast steel shoe is placed and secured to reinforcement with mild straps. The concrete is placed in the form and vibrated. The form is then removed after 3 days, but the piles are kept in position for 7 days. Piles are then shifted to curing site and concrete is matured for 4 weeks before it's actually driven to the project site, where heavy equipment will be used to drive it into the ground. Cast in situ concrete piles. Now, as the name suggests, these are actually made on site. They are quick to install with an integral pile cap and they reduce floor slab thickness. Installed by pre-excavation, elimination of vibration is done, so that means we do not require that much of driving equipment. We are reducing the amount of vibration and stress that is coming from the construction site. The maximum design load is about 75 tons and they can be broadly classified as driven or board piles, as we had already discussed. So the first thing we are going to do is we are going to see how cast in situ driven piles can be subcategorized. So mostly if we see cast in situ piles, they can be cased or uncased. Cased piles can be further subdivided as Raymond pile, MacArthur cased pile, Union metal monotube pile, Swage pile and the Western button bottom pile. Now these divisions can be a little overwhelming right now, but you can easily remember them if you can remember their shapes. They all look different from each other because of their classic shape, and that should help you remember how to categorize them. We are going to look at each of them in detail and study how they are constructed on site. Uncased piles can be divided into 4 types: simplex pile, Franke pile, Vibro pile and MacArthur pedestal pile. Let's first take a look at the cased piles. So the 5 types of cased piles we are going to look at one at a time. The first one was Raymond standard concrete pile. Now this shell is first of all driven into the ground. It has a collapsible steel mandrel inside it and it has a taper. So that means the Raymond standard concrete pile is tapered. That should help us remember it. Usually the length of the pile varies from 6 to 12 meter and the diameter can vary from 40 to 60 centimeter at the top and 20 to 30 centimeter at the bottom. As I mentioned, it's a tapered pile. The pile consists of a thin corrugated shell or casing which is closed at the bottom, and it is primarily a friction pile, which is exactly why it is corrugated. The surface has to be corrugated to induce friction. So this is what it looks like. As you can see, it is gradually reducing or tapered towards the bottom, and it has a corrugated surface which helps to make it a friction pile. If we are trying to go for a deeper pile, in that case the standard Raymond pile is not going to work. We are going to have to go for a tapered, step tapered concrete pile. So this type of the mandrel driven pile has to be made in small parts and then it has to be connected using screw connection. So the cell sections are driven into different lengths. The joints between the sections are screwed together and the pile diameter increases by 2.5 centimeters for each successive shell. The maximum depth we can go for is 36 meters using a 20 centimeter tip. This type of pile can be both end bearing and friction pile. Because the surface is corrugated, it can act as a friction pile, but if it reaches sufficient depth, it can help anchor the building to the hard strata. Hence, it can also work as an end bearing pile. MacArthur cased piles are a little different from the previous example. They are cased, but they are uniform in diameter and do not have a taper. They are made with a corrugated steel shell which remains in place. That is, it is a cased pile. The shell remains. The process of casting is such that the heavy steel casing with the core is driven into the ground. Then the core is withdrawn after desired depth is reached. Then the corrugated sheet shell is placed in casing. Concrete is filled into the steel shell and the outer hard casing is removed after gradual compacting. This is what it looks like. It has a corrugated surface, hence it can work as a friction pile. The Union metal monotube pile. This is suitable for a variety of soil conditions and it can also act as an end bearing or a friction bearing pile. The process is that the pile shell is driven into the required depth with the help of a hammer of comparable size. The shell is then inspected, following which it is filled with concrete, and if there is an extra length of the shell which is jutting above the ground, we can then cut it off to the size that we require. Swage piles look slightly different from the previous examples. In this case, we are going to have some form of a bulb or a plug at the end of it. So that is how it is slightly different from the previous examples. So how do we make it? First of all, the steel pipe, the shell, which has a concrete plug in it at the end of it, a steel core is inserted into it and it is driven into the ground such that we can take the plug and it reaches a certain depth. Once it reaches the depth, the pipe is swaged out by taper of the plug to form a watertight joint. When the shell reaches a desired depth, the core is removed and the shell is filled with concrete. So this is how it works. The plug reaches a certain depth, we create a watertight situation, we fill it with concrete once the shell is removed, as you can see in the figure. The western button bottom pile is similar to the swage pile, but it looks a little different if we see the figure. The end of it doesn't look like a plug anymore, it looks mushroom shaped or in the form of a button. So it is called a button bottom pile because of its particular classic looking front plug. Now obviously it is going to be an end bearing pile because this button or the plug at the end of it helps us anchor this into the hard strata. Now the pile this is using this plug to transfer the load or anchoring the building. So this can go up to about 23 meters and it can take above 50 tons capacity. So the steel pipe and reinforcement base of cast steel are set over the concrete button. The pipe and the button are driven into a specific depth. The corrugated steel shell is inserted in the pipe and it rests on the button. The casing is then removed. Of course, the button remains in its place fixed. Then the shell is filled with concrete. So this is what the process will look like. The shell is inserted, the button is at the bottom anchored, and then the shell is filled with concrete. Category of uncased concrete pile. Now these piles do not use casing. It is used in locations where the ground does not disturb the pit hole with soil or there is no chance of water falling in, and there can be major 4 categories: simplex pile, Franke pile, vibro pile and pedestal pile. The first type, the simplex pile, it can be driven into soft or hard soils. There is an iron shoe at the end of it that allows us to drive it into the ground. We may also alternatively use an alligator jaw point. That way we will not have to leave the iron shoe inside the ground. The alligator jaw point allows us to reuse it multiple times. How do we make it? The steel tube which is fitted with the cast iron shoe is driven into the ground up to the desired depth. The reinforcement is provided in the tube. The tube is filled with concrete and gradually we leave the cast iron shoe in the bottom and the tube is gradually removed. So this is what it will look like, how the tube is inserted. This is the iron shoe which helps us to drive it into the ground, and this is left behind inside the ground. The casing is removed after the concrete filling is done. Now alternatively we can also use this alligator jaw. So it looks very much like the iron shoe, but the difference is it can be opened and then dragged out of the ground. We can lift it up when it's finished, so that way we can reuse this and we do not have to leave behind the iron shoe every time we create the simplex pile. The Franke pile has a mushroom shaped base which acts like a spread footing. A diesel operated drop hammer, which is about 20 to 30 kilonewton force, is used to drive the concrete. More useful where bearing stratum of limited thickness can be reached at reasonable depth. It is best suited to granular soil. The pile diameter, it varies from 50 to 60 centimeter, while the enlarged base may have a diameter of 90 centimeter or more. The pile has a carrying capacity of 60 to 90 tons, so 600 to 900 kilonewton. How do we make this? The process of casting is such that a heavy removable pipe shell is set vertically on the ground with the help of leads. a diesel operated drop hammer is used, and it is driving the concrete, resulting in the formation of a dense plug penetrating the ground and dragging a T-tube with it. When the tube has reached the desired depth, the tube is held in position by cables and the hammer is applied to the concrete, forcing it down and outwards, forming a mushroom shape. Now that is what will help us remember it has a mushroom shape. Now the shaft is formed by introducing successive charges of concrete, ramming each in turn and withdrawing the casing gradually. So this is what it will look like, how the drop hammer is actually used to charge the concrete and create a plug in the bottom, after which the concrete is made. The vibro pile can be categorized as standard vibro pile or expanded vibro pile. The standard vibro pile contains the same diameter all over the length, whereas the expanded vibro pile has a certain extended shape at the bottom, and this can provide greater resistance to load. It can operate in areas where there is low bearing capacity of the soil. The standard vibro pile can be made with 35, 45 or 50 centimeter diameter, and based on the capacity of load that it has to take, and it can go up to a depth of about 25 meters or more. So there will be a bit of a shoe, and once the steel tube is inserted, the concrete is charged, the steel tube is then removed, which is why it is an uncased concrete pile. So how do we make the standard vibro pile? The steel tube is fitted with cast iron shoe and driven into the ground with the help of a hammer. When the shoe reaches the desired depth, we then fill the tube with concrete and we gradually withdraw the tube, hammer in to consolidate the concrete. Eventually the concrete gets filled in without any vacant space in between, and finally we remove the entire tube and we have a corrugated face of the pile. So it will work very well as a friction pile as well. The vibro expanded piles are pretty similar to the normal ones, but they have a bit of an extended plug in the end. So here the tube is fitted with a conical shoe and driven into the ground. The charge of concrete is given and we withdraw the tube slightly and basically use a flat shoe, insert the tube again with a flat shoe into the hole such that we can create a bulged end. And once that is done, the reinforcement cage is lowered into the tube and we can finish constructing the entire tube by filling it up with concrete. So this is that expanded shape that will be formed in the bottom, and we are making this by inserting a flat shoe, as you can see later on, into the tube to create this enlarged bulb. The next type is the MacArthur pedestal pile, and it is used where there is a thin bearing stratum, and the pedestal pile can give the effect of a spread footing, so it will be able to give much greater load bearing capacity. The process of making this is that the core and the casing is driven into the ground. When it reaches the desired depth, we charge it with concrete. The core is replaced into the casing till it lands on top of the concrete. We apply pressure and we gradually remove the casing, and this charge of concrete is rammed out to create a pedestal form. Once this is done, we can then finish up by creating the rest of it by filling up with concrete. So this is the pedestal sort of a end that we are trying to create, on which the entire pile will rest. So this is, as you can see, it is anchored into the hard stratum, so it is an end bearing pile. So those were all the types. Now we are done with the driven piles. So all of these piles are created by using some form of a hammer, where we are using a hammer and driving in the concrete into the shell that we have inserted into the ground. So the shell is inserted, then the concrete is inserted within it to create the pile. Now the next type that we are going to study is not being driven into the ground, it is gradually being bored into the ground. So the process of this construction is going to be slightly different, making this another category of cast in situ concrete pile. This is formed by boring a hole into the ground and then we are concreting it. Now the advantage of this is no heavy pile driving equipment will be required, and a lot of noise that happens in the construction because of this driving will be eliminated. We will have three types which we're going to study today. The first is the pressure pile. As the name suggests, it is actually created with the help of pressure, air pressure. Second is the underream pile foundation, which we had already studied in last lecture, but we will see the process of construction in detail today. And the third is the board compaction pile. So the pressure piles, how are they created? About 1.2 to 1.8 meter long steel tube is sunk into the ground with the help of a boring tool which is working inside. It is gradually boring its way into the ground. Then further sections of the tube are screwed and sunk into the ground. Bored soil is continuously taken out. We clean up the tube. Then a charge of concrete is placed inside the tube and the upper end of the tube is closed. So we are going to use up airtight pressure cap on the top within this already cleaned up tube. Now compressed air is going to help us drive the concrete downward into the pile. Gradually we will be able to fill up the entire pile with concrete following this process. So this is how it works. We are boring our way into the ground, creating this clean tube. Then we are going to give a charge of concrete, and with the help of the pressure cap from the top, we will ensure that the concrete moves down, and then we will have the entire pile created. This is the first type, which is the board pile, board pressure pile. Now the underream pile foundation is the familiar name for you. The board cast in situ pile, this has one or two bulbs in the end. This bulb actually helps us anchor the building better. It helps us take the load. It is particularly useful in types of soil like black cotton soil, where a lot of undesirable seasonal changes happen. That is, the soil actually imbibes moisture, increases in volume during the rainy season, and maybe becomes excessively dry and develops cracks during the summer season. So in those places, underream pile foundation is particularly useful. So it's a very long process through which we make it. Let's stay with me. The ground is first level and the boring guide is correctly positioned. Spikes are fixed and soil inside the tround collar is taken out. Now a spiral auger, and this is what going to help us create this opening, is lowered into the round hole. Flaps are tightened and the auger is rotated to bore a hole into the ground. The auger flaps are then taken out, and then finally we are going to insert into this opening an underreaming tool. This is what gives this particular pile its name. The underreamed pile foundation is named after this tool. So the underreaming tool has a bucket attached to it and has two blades on its sides that is lowered into the ground. When it reaches the correct depth at which we want the bulb, we can use these rotated blades to create a bulb shape opening in the ground, and all the soil that is excavated will fall into the bucket. So this is what it will look like. So the spiral auger had created this opening. Then we inserted this underreaming tool with the bucket at the bottom. So this is going to reach a certain depth. Then these sides of the tools are going to help us create the opening and the soil will fall into the bucket. After this, we can continue creating the rest of the pile. How we are going to do that is, when the bucket is full, we will close the blades, we will take it out and throw away that soil. Then the underreamer is lowered again, and we'll keep repeating this until the size of the bulb is just the way we like it. Once the bulb is made, the reinforcement cage will be lowered in. As you can see here, the reinforcement cage has been lowered in, followed by filling it up with concrete. Gradually, once it is done, the entire pile will be created. Now this is with one bulb. We can also create the underream pile with two bulbs, something like this. Now this pile will be surmounted by a pile cap, but there will be a certain gap left in between. As we had discussed even in the last lecture, this gap has been left to accommodate the seasonal variation in the soil's volume over time. So that during monsoon, when the soil increases volume, we will still have an air gap to accommodate that change. Then comes the board compaction pile, and it is a modified form of the underream pile. Now this cast in situ pile is actually a combination of bored and driven piles. So it has characteristics of both, and the construction process is also quite interestingly a combination of both. So in this method, what we do is, we will do the same process of putting in reinforcement, doing the concreting of the pile. The only difference is that the concrete is placed in first and then the reinforcement cage is inserted or driven into the concrete. So in all the previous examples, the reinforcement cage was introduced first, then the concrete was filled in. But here we are going to do just the opposite. We'll fill it up with concrete, then we'll drive the reinforcement into the pile. So what we are going to do is the bore is prepared with the help of the spiral auger. So pretty similar to what we did in the underream pile. The underreaming tool will be inserted. The concrete will be poured into the pile. It will be filled. The cast iron conical shoe, which is welded with the reinforcement cage, because without that it will be difficult to drive the cage into the already filled in concrete. So we're going to use a cast iron conical shoe, and then we'll drive this reinforcement cage to the suitable depth. Once that is done, we're going to finish up the filling of concrete and let that settle in. So it is becoming a combination of driven and bored pile, because the initial process is boring, where then we are filling it up with concrete, and finally when that is done, we are driving in the reinforcement cage. So those were all the types of concrete piles. Now we'll move on to the other types of pile foundation. The first one we're going to look at is timber pile. This is alternatively another material that we can use. So timber piles can be square in shape or they can be circular in shape, and they can be about 30 to 50 centimeter in diameter, but the length should be such that it should not be more than 20 times its top width. To protect the head of the pile while driving, an iron shoe is provided on the top. So this particular type of timber pile has some steel shoe in the tip so that we can drive it in without hampering the tip of the pile. It should easily be put into the ground, and it will also have an iron ring at the top where we are going to be hammering it to protect the timber from splitting. This will not be able to take as much as the load we were seeing in the concrete pile. It is slightly less. We can take about 20 tons of load. So here we can have different types of shapes, and you can see that there will be some amount of attachment at the top and bottom. This should help us first of all drive this pile in, and we can also protect the top while we are doing the hammering. Steel piles can be of various shapes. They may be made up of a rolled section, any particular fabricated shape, or they can also be sheet piles. So commonly we will have about three main types: H piles, box piles, tube piles, and of course we also have the sheet pile. As you can see, different shapes are possible. H piles are suitable where there is a need to penetrate hard material or rock, and we do not want a particular pile where there is some susceptibility of jetting or coring. So we do not want a pile which can get cracked or damaged while inserting into the ground, because we are dealing with a hard strata. It requires less space for shipping and storing, because H piles can be easily put together and sent in transportation, trucks, etc. And these are often used in the construction of bridges, and H piles are alternatively also used in composite piles. We'll take a look at that soon. Now, box piles are generally used to support a wharf or other sea structures. So if you are creating something in deep water, or there is a lot of silt and there's a tendency of the banks of that water body to slip or slide, we can use box piles in those places. It can also be driven into hard strata, and it also has great lateral strength. The tube or pipe piles are made of seamless or welded pipes, and they can be driven either in open-ended or close-ended depending upon the soil conditions. Composite piles are a combination of two types of materials. So we can use either timber or concrete piles, steel and concrete piles. So let's take a look at the first type, which is the timber and concrete composition. The steel casing tube or steel core is driven into the ground until we reach the suitable depth. The core is then withdrawn and timber is placed in. So we are using one timber pile and inserting it. the core is placed again on top of the timber pile so that we can drive the timber pile to the desired depth. This is exactly why we needed an iron ring on top to protect the timber pile while it is being driven. The core is withdrawn where the charge of concrete is placed on top. We will maintain the pressure. With the help of a hammer, we are going to push the concrete down, and this will actually go and meet the timber and create a concrete pedestal. So where the concrete comes and rests on top of the timber pile, a pedestal will be created, and that will help both of them, that is the timber and the concrete portion, to act together as one composite pile. So this is what it will look like. This is the timber pile portion. This charge of concrete is going to become a bulb once pressure is placed with the help of a core, and then eventually it will form one composite pile which will act together. The next type is the steel concrete pile, where we can use a steel edge section. It's going to be very similar to the previous example, only here instead of the timber pile we are using an edge section which is driven in first and then the concrete goes in. The concrete will be placed such that the edge section actually penetrates into the concrete portion up to about 1.5 to 2 meters. So there will be an overlap between the concrete and the edge section portion, making them act together in the form of one composite pile. Now we have been talking a lot about driving the pile into the ground. So what do we mean by driving? What type of equipment is required for us to drive the pile into the ground? So let's take a look at that. The process of pile driving requires that we use a lot of force to actually drive the concrete or drive the precast pile into the ground, which requires us to use something called a hammer. So the drop hammer is a term which we have already seen in previous slides. So this drop hammer is actually supported on a crane, and this equipment helps us drive the piles into the ground. So there are many types of driving hammers that are available to us, which we can use in construction. The first one is the drop hammer. Now here the hammer is raised by a winch and we drop it by gravity. So it's literally like raising this hammer to a certain height, and from there we drop it, and due to gravity it falls, and that force helps us to drive something into the ground. The second type is called the single acting hammer. Here the hammer is raised with the help of steam or compressed air or internal combustion, etc., and we then allow it to fall by gravity. The third type is the double acting hammer, which employs steam or air for lifting the ram, and then we also accelerate it in a downward stroke. So here not only are we raising it, we are also using mechanism to drive it downward. In the previous two hammers we are using gravity to drop the hammer, but in double acting hammer we are going to use the same mechanism which we used for lifting to also drive it or accelerate it downward. The diesel hammer is a little smaller, it's lightweight, it's more self-contained, self-acting hammer, and it has its application in construction. If you are dealing with smaller sites, this particular hammer can be used. The vibratory hammer helps us to vibrate the driving unit at a very high frequency, which helps us drive it into the ground and is also very useful in settling the concrete. So these are some pictorial representations of the hammer that we just learnt about: the drop hammer, the single acting hammer, the double acting hammers here, and the diesel hammer, and of course the vibrating hammer. Other than these hammers that we just studied, there are several other equipments which are also used for pile driving. We need piling rigs, which are composed of a series of leaders consisting of tabular elements or hard boxes which are fixed and placed on a crane base. We can also use piling winches, which lifts the hammer and piles in addition to supporting it and helps it rotate also. The hanging leader is designed to be hanged from the jib of a crane. The hammer guides help us to prevent disproportionate bending stress development, and it helps us guide and support the hammer, because when we are driving or dropping the hammer, we also need to ensure that the hammer correctly falls on top of the pile or exactly at the position where we intend it to go, which might not always happen, especially if there is a slight tilt in the way we have oriented our hammer. So we need hammer guides to ensure that it falls in the right place, otherwise it can significantly damage piles on site or create other accidents. We also need the drive cap or helmet. Now this is placed on top of the pile. This is what receives the blows of the hammer and it prevents the head of the pile from being damaged. Now in case of the timber pile, we had seen that an iron ring is placed on top of the timber pile to ensure that the top doesn't get damaged. But even if you are dealing with other concrete piles or precast piles which we are driving into the ground, which are prepared in factories, we have to ensure that the top doesn't get damaged. So we can place a drive cap or a helmet to prevent that from happening, and the hammer comes and hits on the top of the helmet. Usually these are made with cast steel and it helps us maintain the axis of the pile in line with the axis of the hammer. Now this is the part of piles. So we have learnt how we can categorize different types of piles. So we have concrete piles, we have timber piles, we have steel piles. Even in concrete pile we have learned different types of mechanisms, functionality, how we can distinguish between driven piles and bored piles, and even within driven piles how we have cased piles and uncased piles. Don't worry, we are going to revisit again the terms at the end of the lecture, so it will be easier for you to remember. But nonetheless, when we have inserted these piles into the ground, we cannot directly start constructing on top of the pile. It's almost like supporting the building on stilettos. That wouldn't work. So we need a level surface which will help us to build on top, and there will be multiple piles which have to act together in a consolidated manner. So for that we require something to bind them together and provide us a level ground. So that is where the pile cap comes in. Pile caps help us create a stable foundation, and it offers a larger area for the distribution of the building onto the piles. So the load of the building, if it has to be transferred onto the pile, it needs a much larger surface in between to help us do that. So this pile cap consists of a rigid, deep, reinforced concrete slab, and the piles are arranged within this cap in such a way that the load is symmetrically distributed into all of these piles. So uniform distribution of load has to be ensured from the superstructure to all the individual piles. So we'll have to arrange the piles in a particular order and in such a way that the center of gravity of that load is equally distributed through the pile cap into all of the piles. So this pile cap slab is made with uniform thickness and it attaches itself to all of the piles underneath. The area of the pile cap is divided into a framework of rectangular beams along with main reinforcement. So definitely RCC pile caps are going to have reinforcement within. Now what are the functions that this pile cap is playing? First of all, it will distribute the single load that is coming in from the superstructure equally over the pile group. So whatever is the number of pile that we have decided is needed to transfer our load, this pile cap is going to uniformly distribute the load to all of them. It also provides lateral stability of individual piles, holds them in position. It provides necessary combined resistance to stress which is developed from the superstructure and the ground, and it transfers the building load to the foundation. So we can have several arrangements of piles within the pile cap. We can have 2 piles together, 3 piles together, 4 or 5 piles together, and so on and so forth. Based on the way we arrange our piles, the shape of the pile cap will also vary. Normally, if you may kindly note the 3 pile cap, we'll see that we are not going for a classic triangle. We are not placing the pile within a triangle. We are actually chamfering the edges. Now why we are doing this split at the side is because it is very difficult for us to cut corners like this when we are dealing with foundation construction. This can become problematic during construction. It is much better to go for a chamfered edge, and it is created in such a way that there is sufficient cover between the reinforcement that is placed inside and the concrete. So certain gap has to be ensured. We had studied this even when we were doing the grillage foundation in the last lecture, where we had learnt that a proper concrete cover has to be given to ensure that the reinforcement at any point doesn't become exposed, which may lead to corrosion. So proper cover has to be given, and we have to chamfer the edges because it becomes very difficult to create triangular corners in the foundation construction. So different shapes and sizes of pile caps will have to be constructed based on the number of piles we have, the type of load coming in. So this of course requires for us to ensure that we've selected the right type of reinforcement as well, and some amount of knowledge of RCC construction will be required for this. So structural analysis is needed. Now when the piles are being arranged under the pile cap, as we just saw, we can have 2 piles, 3 piles, 4 or 5 piles. Now how do these piles actually work together? Does it mean that whatever load is coming in from the superstructure, I just divide it by the number of piles underneath and that should solve my problem? Not exactly. There is a group action in piles. Piles together work in such a way that it's not exactly equal to the load divided by the number of piles. So how do we solve that? There is something called the Feld's rule, which helps us understand the efficiency of a group of piles. Let's take a look at that. Now whenever there are several closely spaced piles acting together, the bearing capacity of the pile group may or may not be exactly equal to the sum of the bearing capacity of individual piles, because there is a group action that is happening between all of them. So they are holding hands in a particular order, and that will not ensure equal efficiency from all of them. So the efficiency of the pile group depends on several factors. The first thing is the type of pile that we are using. What is the length, diameter, what material have we used? We have learned so far that different types of concrete piles, timber pile have different load bearing capacity. So definitely the type of pile that we have selected will be the first criteria that will determine how much efficiency this group is going to have. The second is how we are spacing the piles, how they are arranged, what is the number of them. So the total number of the piles is the next criteria. What are the number of rows that we have arranged it in? So all of these parameters are going to influence the efficiency of the total pile group. Now Feld's rule is this particular formula. It's being said that the efficiency of a pile group can be determined by this formula, which is QS. This is the load carrying capacity of the entire group of friction piles. We are dealing with friction piles here, let's say, and that is equal to N, that is the number of pile, QF, which is the load capacity of each friction pile within our group, and NG is a factor of efficiency of the pile group. Now this will vary depending upon the number of piles that are there in a particular arrangement. So this percentage, where we're going to get? Right here. So the rule of Feld says that 1/16th on account of effect of the nearest pile in each diagonal or straight row of a pile in question is going to be taken as the factor of efficiency of that piles in the pile group. So whatever is the number of piles we are using in a group, we are going to take 1/16th on account of each of the nearest pile in the diagonal direction or the straight row. So if we are having 2 pile in a group, the efficiency is going to come as 15/16, so 54%. If we are dealing with 3 piles in an arrangement, so it's a triangular arrangement, we have 3 here, so 97%. If we have 1, 2, 3, 4 pile, then that number will be 82%. And if we have 1, 2, 3, 4, 5 pile, it will be 88%. So based on this component NG is going to vary depending upon the number of pile we have in the arrangement, and that should be helping us calculate how all these piles in a particular arrangement is going to work together and what will be the total efficiency of this group. Now sand piles, as we had learnt in the beginning of the lecture, are used mostly as compaction piles. So they are 20 to 40 centimeter in dia. They are formed with the help of an auger. We are forcing a pipe in and then filling it up with the required amount of sand. We are compacting the sand and then placing the concrete. So usually they take up about 100 tons per square meter or more of load. So how do we make them? The hole is formed with the help of an auger. or a pipe with a closed end. We fill it up with sand. Sand is rammed. Water is added so that we can compact the sand, because as the name suggests, it's a compaction pile. And the top of the sand pile is filled with concrete. Now sheet piles. Sheet piles are thin piles which are made up of concrete, timber or steel. They are driven into the ground to stop seepage of water. So if you are trying to create a watertight place somewhere for construction purposes, we can use sheet piles. They are not meant for carrying vertical load. So it's mainly to create airtight spaces or to create a division between two areas. It's not really meant to carry any vertical load from superstructure. So we don't build anything on top of it, but we build within it or alongside it. This can be either made with concrete, timber or steel. So there are various shapes, sizes that are possible, and depending upon the type of pile we have, we are going to use different types of interlocking mechanisms. As you can see, there are V-joints, there are grooves or tongue grooves, and there are also dovetail joints. So the way we join the sheet piles will vary depending upon our design. What are the functions that sheet piles play? It encloses a site and prevents escape of loose subsoil. It can retain the sides of trenches even when we are doing general excavation for other constructions. It can form watertight enclosures. It can create retaining walls in docks, wharfs or other marine structures. It can protect riverbanks. It prevents seepage below dams and other hydraulic structures. It can help us confine soil and increase the bearing capacity of soil, and also protect the foundation from scoring action of nearby water bodies. So these were all the types of piles that we can use in deep foundation. Now the last two types that we are going to study today are cofferdams and caissons. Let's quickly take a look at them. Now cofferdams are structures which retain water and soil and allow us to enclose a certain area, and within that area then we can pump out the water and we can excavate it dry to create this watertight empty space for further construction. So cofferdams are very useful if we are constructing bridge piers and other support structures within water. So let's say we have to do a bit of a construction inside a water body. So we're going to have to create an airtight, watertight, empty space on which we can do the construction. That's where cofferdams are going to be useful. So first of all, we are going to use sheet piles, and we are going to support this with the help of whalers, internal braces, cross braces, and then we're going to create this cofferdam within it. These normally are dismantled after the works are done, so they are not permanent structures, and they are usually constructed within water, and the sheet piles are installed using pre-constructed templates that allow us to correctly position each sheet pile within a particular area. So we can use different types of members for the cofferdam, in the sense that we can have the cantilever sheet pile. Here there are no members that are supporting these sheets. They are being held in position in cantilever format. They are holding each other. We can also use braces, struts to support the sheet piles in position. Here we have struts supporting the sheet piles. And we can also have embankment protected cofferdams or double wall sheet pile cofferdams. So here we have a double pile. So there are two layers. Other than this, we can also have a cellular cofferdam, where each cell, each of these cells that we see is filled with some granular material. These are all filled up. So this is a cellular cofferdam. The last type of deep foundation we will study is the caisson foundation, and these are watertight structures which are used for retaining water in order to work on foundations, bridges, piers, etc. The water is pumped out to create a completely dry work environment, and some caissons can be open air, whereas the others can be such that we use compressed air to keep mud and water out of it. Now installation is done in different mechanisms depending upon the shape or the mechanism. We can either call a caisson box caisson, open caisson or pneumatic caisson. Now unlike cofferdams, caissons are permanent structures. So after the construction of the pier or the bridge is done, we're not going to remove it. So here the first example is of a box caisson. So as you can see, there are concrete walls which are filled with sand within it. So this is what it will look like in plan and in section. The next are open caissons. So these examples of circular, rectangular, twin circular, double well, double D, twin hexagonal or twin octagonal are open caissons. So these are kind of like well foundations. So from the top it will look like a well. And the other type are pneumatic caissons, where we can use compressed air to ensure that mud and water doesn't enter this space. So these were all the types of deep foundation. We are going to revisit the type of pile foundation because we learned a lot of types. So let's revisit it to revise. First of all, pile foundation can be concrete pile, which means it can be precast or cast in situ pile. Cast in situ piles, which are made on site, can either be driven into the ground or they can be bored into the ground. Driven piles can be cased or uncased, that is they may have a covering or not. Bored pile can be pressure piles, under-ream piles or bored compaction pile, which is a combination of bored and driven both. Timber piles can also be made. Steel piles can be edge pile, pipe pile or sheet pile. And composite piles can be a combination of concrete and timber or concrete and steel. So those were the types of pile foundation that we had learned today. Other than that, we also took a look at cofferdams and caissons. These are the books we can revisit to further study them in detail. So today we learned about deep foundation. With this, we can say we've done with module 1, that is we've studied all the types of foundation. We started with shallow foundation, took a greater look at black cotton soil foundation, the different calculations needed to calculate the design footing size and depth in shallow foundation, and finally we ended with different types of deep foundation. So with that, we are ending our foundation and we will now move our way upwards into the building and go towards masonry. So thank you everyone. See you in next lecture.